Okay, this lesson is the ideal gas law. We're going to consider what we've learned already, the gas laws of Charles, Boyle, and Gay-Lussac, and the fact that we use kinetic molecular theory to explain those laws. Those laws describe the behavior of gases, and truthfully, those laws are most accurate in their calculations, in their results, when the gases are under low pressure and high temperature. These are referred to then as ideal conditions. We make assumptions in the kinetic molecular theory that there are no forces of attraction or repulsion between the particles, that the collisions are perfectly elastic, so no loss of kinetic energy, that the volume of the gas is really small and negligible, really, compared to the volume of the container. So we make those assumptions and work with Charles, Boyle's, and Gay-Lussac's law, and find that the answers that we get when we do those calculations are most true, so most correct for our experimental results, when the gases are at low pressures and high temperatures, which really, that is most of the gas samples that we work with. Now, let's look at why that is. For low pressure, you'll see the diagram down here on the left. You can see that under low pressure, so there's just one weight here, the gas occupies a large volume. So low pressure, large volume. We see the inverse relationship of Boyle's law. At higher pressures, right, significantly higher pressures, this volume would be quite small. So remember this assumption that the volume of the gas is negligible compared to the volume of the container. We assume that in KMT. And when you have a large volume, so in other words at low pressure, the actual space that the particles themselves occupy, and I know I've clustered them all together, but I'm just trying to show it as a fraction of the volume of the container. You can see that the size of the green square here is quite a bit smaller than the rest of the volume of this container. Whereas at very high pressures, under low volumes, or we'll have low volume, and the gas particles themselves still occupy the same space, whatever that is, but now that green square is a much greater percentage of this small volume than it was in this case. So when this is the situation, we find that, yeah, this green square volume is you can basically ignore it. And that's what we're doing when we make the assumption of kinetic molecular theory. So at higher pressures, we'll find that that assumption breaks down, and therefore the results of our calculations won't be as accurate to the experimental results as they should be. Now, what about at temperature? Well, low temperature, remember temperature is related to the average kinetic energy of the particles. So if you're at a very low temperature, the particles have a pretty low kinetic energy, and that means that they're moving slowly. So as they come in contact with one another for a collision, following their Brownian motion, the intermolecular forces have more opportunity to attract, and so the molecules will interact, and that becomes more significant the lower the temperature is. At higher temperatures, with high kinetic energy, the particles are moving so quickly, they easily overcome any intermolecular forces, and so we find that those are less significant. So when we make the assumption that there are no forces of attraction between particles in KMT, it's really not a good idea to make that assumption at lower temperatures, but it is fine at medium to higher temperatures, as long as the particles have enough kinetic energy that their intermolecular attractions are not very significant. So essentially then, we have a set of ideal conditions: high temperature and low pressure. So most of the gas work and calculations that we're going to do will be at atmospheric pressure and maybe the top of a mountain or at sea level. We'll be working with temperatures, in a freezer or in standard ambient temperature, so room temperature, or perhaps at higher temperatures when the gases have been heated. And so really, for our calculations, we're going to assume ideal gas behavior, and that's where all of these formulas give us the most accurate results. So we'll move forward now looking at So we'll look at Avogadro's law. Imagine blowing up a balloon. You have a deflated balloon, and what do you do to blow it up? Yes, you blow air into it. So what are you increasing specifically when you are putting more particles of gas into the balloon? Well, you're increasing the amount of substance. Yep, so as you increase the amount or moles, the volume of the balloon inflates. So we see that those variables vary directly. And that's Avogadro's law, that volume varies directly with amount at constant temperature and pressure. If you use STP conditions, 273 Kelvin and 101.3 kilopascals, and look at 1 mole, or I should say 1.00 moles here for some sig figs, 1 mole of any gas will occupy 22.4 liters of gas. And so that is considered the standard molar volume. I'll be using that set of data in a moment when we go to calculate the constant for the ideal gas law equation. So the formula that we're going to be working with mainly from today's lesson involves a combination of all the gas laws. So volume varies directly with amount, directly with temperature, that's Charles' law, and inversely with pressure. If I'm going to introduce an equal sign, then I need to introduce a constant. I'm going to use capital R for the constant because that's the letter that's given to the ideal gas law equation constant. In order to simplify this equation, I'll get rid of the quotient on the right side, so I'll multiply by pressure on both sides in order to come up with a version of this formula that's a bit easier to remember. And I did swing the lowercase n out in front of the constant. And so here we have the ideal gas law equation, PV equals nRT. So you need to memorize this formula, PV equals nRT. Now we need to determine the value of the constant R, so I'm just going to work up here on the right and recopy PV equals nRT. Now go ahead and isolate R and then substitute these values for T, N, and V and determine R. Okay, so hopefully you came up with 8.31. So this is a constant. Now let's check the units of that. So pressure was measured in kilopascals, volume 22.4 was measured in liters, the 1 was moles, and the 273 was Kelvin. And so here's the value of R, 8.31, when pressure, volume, and temperature are measured in these units. So we say R equals 8.31 kilopascal liter per mole Kelvin. So since R is a constant, every time you use some version of the ideal gas law equation, you always are going to know R. Pressure must be in units of kilopascals if you're going to use this value of R. Volume must be in liters when you use 8.31. Temperature is always going to be in Kelvin, N will be in moles, right? And that allows us to use this value here for R. So if your pressure is not in kilopascals, if it's in atmospheres, it wouldn't be wrong. It's just that you can't use 8.31. You need to calculate a different constant. So I would recommend in these problems that you stick with the SI units of kilopascals and liters and for pressure and volume, and then you can always use this value of R. Okay, so here's a sample problem. A balloon has a volume of 425 milliliters at 22 degrees Celsius and 102.0 kilopascals. What amount of gas is present in the balloon? So let's think about this. We have a balloon, may help to draw a picture, right? We know the volume, we know the temperature, and we know the pressure. So we're being asked to find the moles. So this is not a combined gas law equation question. We're not being told that this balloon's going to be put in the freezer or fly up into the sky, and now we're being asked what the new volume of the balloon will be at a different set of temperature and pressure conditions. We're just being given this sample. The air's in the balloon, the gas is in the balloon, and with that volume, temperature, and pressure, how many moles of gas are in the balloon? So here's where the ideal gas law equation can be very useful. So when you think of the formula, PV equals nRT, we know pressure, volume, and temperature. You always know R, 8.31, and so that really lets us use this formula to solve for moles. So go ahead and list the actual given data, make any adjustments to the units that you need to do, isolate n in this formula, and substitute and solve. And then check for sig digs at the end and write the proper units. Okay, so you'll see I did exactly that. Converted the volume to liters, temperature to Kelvin, reminded myself of the value of the constant, isolated n by dividing by RT on both sides, substituted and solved. Now in terms of sig figs, I rounded to 3 sig figs. I see 4 here, 3 here, 3 here, and 3 here. Just because there were 2 here when in temperature originally, when I'm adding the 273, there's no digits after the decimal and no digits here, so there's no digits after the decimal in my Kelvin temperature. Now I'm going to use that Kelvin temperature in multiplication and division, and so I now consider the sig figs in these measurements. That's why I'm at 3 sig figs in the end. Okay, let's say the balloon, the gas in the balloon is actually helium. So what's the mass of helium in the balloon? You know how many moles there are? What's the mass of helium in the balloon? Okay, so using factor label and molar mass, I'm able to convert moles of helium to grams of helium and come up with 0.0707 grams. Of course, if you wanted to use a formula, N times capital M, amount times molar mass, that would be fine too. So just to refresh, I solved this problem by first finding the moles, and then I found mass. So what if, in given that problem, we weren't asked for the moles in the first place? What if we were asked for the mass right off the bat and told that it was helium? Well, I'm going to suggest to you that you could take the formula of mass over molar mass and substitute that in to the ideal gas law equation. So the m over m is going to replace the n here. So PV equals lowercase m times r times t over capital M. And then when we multiply by capital M on both sides, we'll end up with MPV equals m lowercase m RT. So I'm going to suggest to you that that would have been an even faster way to solve if we had this derivation of the ideal gas law in our head. We could have isolated for lowercase m here by saying MVP over RT. And then if we'd have to be told it was helium in the balloon right off the bat, but then we could go and substitute our molar mass right away, the volume, our pressure, the value of R, and our temperature, which I think was 295, and we would come up with our mass in one step. So feel free to use this version of the ideal gas law equation to make a two-step problem be only one step. Okay, finally, there's one more derivation of this formula that will be very useful in certain problems, so you need to know this one. I'm taking that molar mass and mass version of the ideal gas law equation, and I'm going to set up a situation where I can incorporate density into the formula. So right now we have lowercase mass in the numerator on the right side. I'm going to divide both sides here by capital V, and you'll notice what I've set up is a situation where I have mass over volume on the right side of the equation. So I'll be able to replace mass over volume with capital D for density. So I have dRT on the left side. And then I can cancel the V's, and so I have MP, or if you prefer PM, doesn't matter, equals dRT. So either of these here are fine. So we have a derivation now, we have a formula, a version of the ideal gas law equation that involves density. Notice mass and volume are not required. You could find the density of a gas. So for example, find the density of, let's say, CO2, carbon dioxide gas, right? And let's say at SATP conditions. So go ahead and find the density of CO2 at SATP conditions. I'm asking you to find the density. You always know R. It's CO2, so that means you'll know the molar mass. And SATP conditions, just look those up if you don't remember, but that'll tell you the pressure and the temperature values. Okay, and so you'll see that I've isolated D in the formula, substituted the pressure, molar mass, R, and T, and come up with 1.78. Now I know this 100 looks like 1 sig fig, but it was defined as standard ambient pressure, and so I'm taking all those values to be significant for that reason, so consider that as 3 sig figs. Now what about units? Well, that 100 is measured in kilopascals, the 44.01 in grams per mole, the 8.31 is in kilopascal liter per mole Kelvin, and the temperature is in kelvins. So have a look at what cancels here. Kilopascals, moles, Kelvin, and that leaves us with grams per liter, which is a mass per volume unit, and that makes sense for density. So, in summary, we had PV equals nRT, MPV equals mass times R times T, and PM equals DRT. So you will need to know all three of those formulas, and you'll find them very useful throughout the problems.